Assalamu alaikum. Today I'm going to show you how to process a panel regression analysis in Stata. First, I'll show you the data which I've taken. I've taken the data from KSE 100 index of non-financial companies for the period 2011 to 2020, that makes up to 10 years. So here I've taken the 5 variables. Let me explain my variables. ROA is my dependent variable. Short-term borrowing is my independent variable. Leverage, size and growth, these three are my constant variable. I will test the panel regression analysis. Panel regression analysis can only be done when there are firms and years are simultaneously. So we can have a I, which is our companies or firms, and T, which are years of in our model. So how to test it in the panel regression on Stata? It is very important to test the regression assumptions beforehand. For this, let's start with our first step. Go to Stata, go to File and import your Excel workbook. You can also choose any other format if you have saved in it, but I have saved my data in Excel format, so I click on it, browse the data where you have saved it, and select import first row as variable names. This is because I have saved the variable names in my first row of Excel sheet. When I click on it, it will take the variable names completely and make the data in starting from another row. Then click OK. To test the regression assumptions, first we need to check the pool regression. For this, I'm writing the command, that is reg select your dependent variable. It is very important to select the dependent variable first and then click your independent and constant variable, because otherwise it will not show the relationship between dependent and independent variables. After clicking your desired variables, press enter. Here you can see the results has been shown where the coefficient, standard errors, t-value, p-value and confidence interval values can be seen. The r-square value in this model shows that 22% of the data or model is being explained by these variables. Rest 78% has not been explained, which becomes our error terms. So there may be more variables, but for this video I have taken only these 5 variables. Okay, what we need to do now? We need to check if there are outliers in our data. For this, I am checking it through histogram. You can go to graphics, histogram, select the desired variable. I am checking the outliers for ROA. Go to density plots and select add normal density plot. Click OK. It can be taken it from the command, which is histogram ROA comma normal, or you can go to the descriptions I have mentioned. Here you can see the graphs appeared, which shows that the data is very peaked. That means the data is not normal. For this, first we need to normalize our data. I'm normalizing it through standardization method, or removing the outliers through standardization method. Standardization method can be applied by firstly check our descriptive statistics. Descriptive statistics are mean, minimum, maximum, standard error values. For this, the command is summarize, select all the variables for which you need descriptive statistics and click enter. Here you can see that observations against each variable, mean, standard deviation, minimum and maximum value can be seen. Now what you need to do is you need to standardize the variable, right? How you can do it? From the command egen, then name your variable whatever you want. I am naming my variable as ZROA is equals to std bracket open, select the variable ROA bracket close, press enter. Now a new variable has been generated, which is a standardized variable. Here you can see that it shows that it is a standardized value variable, right? Now what you need to do is you need to write replace, select ROA is equals to the mean value. We are replacing the extreme values in our data set which are greater than 3, right? For standardization, we take a scale of -3 to 3, right? If the values are greater than 3 or lesser than -3, then we call it as outlier or extreme values in our data set. So I am removing those extreme values with our mean value, which is 0.08575593, right? Press enter. It shows that three real changes has been made. That means there were 3 extreme values that were greater than 3 standardized value name, right? We reselect this command and change our scale to -3, right? I've mentioned that we take the scale of -3 to 3, right? So I have taken the 3 value, or and it showed that there are 3 extreme values that were greater than 3 standardized number value. Now we'll change the values of which are lesser than -3. Click enter, and here it again shows that 3 real changes has been made, which means that there were 3 extreme values which were lesser than -3 of standardized value, right? So here the outliers pretty much have been removed. We'll check it again from the histogram. We can select the command which we have processed earlier and click enter. It shows a pretty much distributed distribution now, but we can also test it from command as well, which is swilk, select the variable ROA, and it shows that the probability is lesser than 0.05. If the probability is lesser than 0.5, that means, or 5%, that means our data is not normal, though our graphical representation shows that it is pretty much normal, but our test shows that it is not normal. We have tested it from Sharpio Wilk W test. So how we can normalize our data? We can there is a method of change distribution method, which we'll use it from SPSS. Then go to the data, copy the data of ROA and paste it on SPSS sheet. Here I'll delete this row because ROA is not a number. Go to variable view, rename the variable as ROA. It is showing in strings, but we need it in numeric numbers. Click numeric and click OK, and select let's say 2 to 3, 4 decimal places, and you can see that now it is in numeric form, right? Okay. We are changing the distribution to make the data normalize, and we are taking only dependent variable here. You can normalize your other variables if your results shows any error or something. Okay, go to transform, go to rank cases, select the variables and select rank types to fractional ranks only and deselect the rank. Continue and click OK. It created a new variable which is RROA. Here, go to compute variable, go to function group and select inverse DF, and then select the IDF normal. Here you need a probability, which is the fractional rank, mean of the variable, standard deviation of the variable. Because we have replaced our sum values with mean, so our mean might be changed by little value, so we'll check our descriptive statistics again. Here the mean value shows that it is slightly changed from the previous value because of the 6 changes made in the data. Okay, go to this, select the fractional rank functions we have just created, fractional rank row. Then you need mean. So copy the mean from here and paste it, right? And then copy the standard deviation and paste it over here. Name your variable as, let's say I am naming it as TROA, and click OK. it is giving me warning. Now why it is giving me warning? You need to go to the data sheet again and see in your fractional rank column if any value is equal to 1 or greater than 1 in it. Here you can see that it is 1, and corresponding to it there is no value, which we created a new variable. That means this value is very abnormal in this fractional rank. We'll just copy the value above and paste it over here, or you can paste any other value because it is the abnormal value in our data, or it might be an outlier in our data. Okay, I didn't mention that I have taken the data from Stata because we have removed the outliers from it. That's why I have taken it from Stata, because the fractional rank can only be generated if the outliers have been removed. Otherwise it will show that the 1 values again, which just showed in this, right? And I'm going to process the compute variable again. Same mean standard deviation, because there's nothing has been changed right now, and I'm naming it again as NROA and click OK. Now it didn't give me any warning right now, and created a new variable. Now you can see that in new variable of NROA it is showing a value now, where previously it was showing only dot. Okay, copy this data from SPSS and paste it in the data sheet of Stata. Paste it over here and rename the variable as, let's say I'm naming it as NROA. Okay, so what changes have been made? Now I'll show you that what has been changed. I'm making a histogram of new generated variable, which is NROA, and you can see the difference, that it is completely symmetrical distributed. And you can test the normality test again, which is shows normality test for the new created variable, and it shows the values above 5%. That means our variable is now normal. Okay, so we have achieved the assumption of normality. Now let's move on to the multicollinearity. Now how can we check the multicollinearity? Multicollinearity, first we need to process the pool regression again with the new generated variable, that is NROA, right? Okay, now the command for the multicollinearity is VIF. Now VIF shows that the value mean VIF is lower than 5%, 5 or 10. It can be 5 or it can be 10. It varies researcher to researcher. You can take the literature background for your analysis, but since it is lower than 5, so I can assume that there is no problem of multicollinearity in our data. You can also test it from correlation metrics. For this, the command is correl, select your variables, and you can see that all the variables are not closer to 1, because for interpretation of correlation matrix as the closer the value is towards -1 to 1, the higher the correlation among them. So there is no such value which is very closer to 1 or -1. You can also have a correlation matrix which provides you the significance. For this, you need to go to statistics, go to summaries table, go to summary and descriptives, then select the pairwise correlation. Here you need to select all the variables, like I'm selecting it in proper arrangement, and select the significance level for displaying with a star. You can have a significance level of 1%, 10%. It is your own choice. Click OK, and now it is showing us that this value is significant with pairwise significance. Okay, since we have no multicollinearity issue, we don't need to change it or transform variables, because if there were highly correlation among the variables, then we need to transform the highly correlated variables. Let's move on to second assumption of the regression, that is heteroscedasticity. For this we need to process the pool regression again and then process the head test, right? Head test shows you the, basically heteroscedasticity provides you the unequal variances in the data. If there are unequal variances in the data, that means there is heteroscedasticity in our data. So to test this, we are testing it through head test command. Here you can see that the value is greater than 5%, which means there is no heteroscedasticity in our dependent variable. We can also check the heteroscedasticity in our independent variable. For this, the command is head test RHS fstat, and you can see all the independent variables or constant variable now showing, and it shows that there is no hetero in our data. You can also test the hetero from another command, which is estat im test, and all the p values are greater than 5%, which means there is no hetero issue in our data. However, if there is hetero in our data, you need to transform your variable. How can you transform the variable? I am just showing you an example. However, there is no hetero in our data. You can just write the command of ladder and the selected variables. Mostly we remove the heteroscedasticity from the dependent variable. So I'm selecting the ladder command with our dependent variable and click enter. Here all the transformation types can be seen. I can show you a single transformation for our dependent variable, which can be like gen. I am naming my new variable as TROA is equals to, copy the formula from here and paste it. Now it created a new variable. You can see from the data sheet of Stata that a new variable has been created, which is the square of our original variable. Okay. However, we don't need it now. You can also take the cubic identity, square root, log, whatever you want, but it is only when there is hetero in our data, or if there is the hetero is not removing from your data from any of this transformation, then you need to just directly run the GLS method, which is generalized least square method, or random effects, which I'll show you later on. Or the second method is robustness check. How you can check a robustness is select this command of pool regression and place a comma and write robust. It will show you the robust regression of your, which is the linear regression, and this will be your final output result in case if hetero exists. In our case it is not existing, therefore we are not taking it as our final result. Let's move on to our fifth assumption of autocorrelation. Okay, autocorrelation is the correlation among your error terms. Like we have 78% of error terms in our data, that means there might be autocorrelation in our data. So how to test it? We'll test it from Durbin-Watson test. With the command for it is you need to again process the pool regression, then generate the time variable, which is gen time is equals to underscore n, click enter, then t set time, TSSET time, press enter. It show you the time variable, that is 1 to 670. Our observations are basically time variable. Then the command for checking the autocorrelation is estat d Watson, that is the Durbin-Watson test. So how you can interpret this? You can interpret it as there is existence of autocorrelation. The closer the Durbin-Watson value towards 2, the lower the autocorrelation in the data. hence it is the value here showing a very lower than 2. That means there is autocorrelation problem. You can also test it from another test, that is estat b god fray comma lag 1. This is the push Godfrey test, LM test, and it is also showing that there is a serial correlation among our data, and we need to remove it. And how you can remove it? You can remove it from the price Winston command, and the price Winston command is you need to reselect the pool regression and place the price, and in the end place comma croc. It is now showing that previous autocorrelation value was this, and now after transformation it is now this. That means our autocorrelation have been totally removed from our data. Now finally we have achieved all the regression assumptions, and now we can move towards the panel regression. For this you need to go to statistics, go to longitudinal panel data, and go to linear models, then select linear regression. You need to select the dependent variable. In our case we have transform our data, and so we will take an ROA and independent and constant variables of short-term borrowing, leverage, size, growth. Okay, go to panel settings, select the panel ID. We haven't created the panel ID, so first we need to create a panel ID, which you can create it as egen company code is equals to group, and select the company. This is your company ID. Okay, now company ID has been generated. Go to statistics, longitudinal panel data, go to linear models, select linear regression, and select the dependent variable. This is an ROA in our case, and select all the independent and constant variables. Go to panel settings. Panel ID in our case is now company codes we have generated, and time variable is years. We are not taking time because years are the time variable in our data. Click OK, and click I mentioned GLS method, that is generalized least square method, previously in heteroscopicity correction method. When you have hetero in your data and there is no way to remove it, or it is not removing from any way, then you just need to process the GLS method, right? I am showing you, otherwise we might not need it right now, but I'll show you how to do it. Press GLS random effect method, click OK. Now the results are giving me from random effect method. We can also test our result from fixed effect. Go to gain, statistic, longitudinal panel data, linear models, linear regression, and select fixed effect method. Click OK, and there is a slight change in the p-values of both results, right? Here you can see that size is giving significance. However, in fixed method, size is not significant. Rest all the variables are significant, and there is a difference of coefficients as well, right? So how you can now just make a decision which method is good? For this, you need to check it through Hausman test. How you can process the Hausman test? You need to store these estimates. How you can store it now? For this, the command is estimates store fixed, because I have processed the fixed panel regression earlier, so I am storing the fixed panel regression results first. Then select the random effect result and process it again, and store its estimates as well with random. Okay, and now you need to process the Hausman test. Go to statistics, go to post estimation, select the specification, and diagnostic good fitness test. Select the Hausman specification test, click launch. We are testing it against the fixed results we have just processed. Click fixed, and you need to leave it empty, this column. Click OK. And now the Hausman test has been generated, which shows the p-value of 0, which is less than 5%. That means we can use the fixed effect. If the p-value is less than 5%, we will take the results of fixed effect. That means it is more suitable for our model, this fixed effect result. That means this fixed effect result is more suitable for our model instead of random effect. We'll mostly take the random effect result when there's a existence of hetero or any other type of violation to regression assumption, right? But since there is no regression violation assumption in it, therefore we have tested the Hausman test, and Hausman test suggested that fixed effect is more suitable for our model, right? So here we are done with our panel regression assumptions and panel regression processing as well. Hope you liked the video and you have just got the idea which I wanted to convey. Thank you.